This is Mark Markey at the University of Alabama, professor of aerospace engineering and mechanics. I want to give a short overview of the critical plane approach for multi-axial fatigue. I want to give an overview of it. I want to describe when we need to use it and what the modules might be if we were to construct a flow chart. We won't go into a lot of the detail, but we'll give kind of this overview that I think will be reasonably understandable. Now, I will assume that you have some knowledge on fatigue already, and maybe even some idea of plasticity, particularly for multi-axial plasticity. Alright, so people have been interested in multi-axial fatigue for a while. It's really started to take off in the kind of the early 90s, and it still is of interest today. People are still working on this, trying to figure some things out. There's a couple different approaches for it, but the one approach that I want to describe here is what we call a critical plane approach. I think it might be easiest to describe if we just start out looking at a typical multi-axial state of stress that we might see in a component. Now, fatigue damage is often a surface phenomenon due to slip systems and intrusions and extrusions of the material. So typically we would have a state of stress that would be planar. Now it may not be fully plane stress. Plane stress kind of depends on having zero stress through the thickness, but if we're on the surface of a component, then we're reasonably in that situation, as long as the gradient into the depth of the component of the stress field is not too severe. So a typical multi-axial state of stress may look something like this then, where we have maybe two directions of sigma x and sigma y normal stresses, and maybe a shearing stress tau xy. Now, if we were thinking of this in a static stress analysis situation, we would take this stress state and maybe construct a Moore circle. Let me draw that over here. We have our sigma on our tau axes, and I'm going to draw a circle, and then I'll put the dots in for it here in a moment. And so maybe this is the center of the circle, and maybe this is our sigma x tau xy point. Maybe this is our sigma y comma minus tau xy point over here. And we would think, and we would look at this would be 2 theta p, and often this material somewhere at the angle theta p, the principal angle, we would find our principal stress state. Maybe that's sigma p1, and here's sigma p2, and 45 degrees from it would be our maximum shearing stress state in the material. And this would be for the planar, the in-plane shearing stress state. You have sigma average all the way around, and we have our maximum in-plane shearing stress, tau xy maximum. That would be equal to the radius of the circle, and this would be sigma average for the normal stresses here and here. Again, this is the case for the static stress state. Now, if these stresses change with time, that's how we get fatigue. They increase and decrease. We have stress reversals, or strain reversals that give us damage. If these stress components are proportional to one another, then the directions of the principal stresses and maximum shearing stress remain fixed. Let's write this down. For proportional loading, what I mean by proportional loading is, for example, if we were to look at a phase space of sigma versus tau with time, proportional loading, all of those components stay constant. So if we have a reference stress state, we have a changing function of time multiplied by that reference stress state to give us our stress as a function of time. Well, for proportional loading, directions of principal stress remain constant. And the maximum shearing stress state as well. Now, adding to kind of the complicated nature of fatigue is that some materials are sensitive more to shearing stresses and strains. Some materials are more sensitive to normal stresses and strains, depending on their internal makeup. Some materials are even sensitive to normal stresses and shearing stresses, depending on how small little fatigue cracks are or the slip systems are. So this can even change with the amount of life fraction that you've already used up for micro crack initiation and micro propagation. Very small development of very small cracks. Well, what we would do if we had a proportional loading case and we had either a normal stress sensitive or a shearing stress sensitive material, for proportional loading these remain fixed, so we can just do the analysis on these stress state depending on our damage parameter. So we would do our fatigue analysis here, or we would do our fatigue analysis there. And so in other words, we can identify immediately where our critical plane is at. The critical plane being the plane that would experience the most damage in a loading history. Now, if our stresses are not proportional, if we have non-proportional loading, then we would not know ahead of time where our critical plane would be, because the directions of principal stress, directions of maximum shearing stress could change with time. So we need to have a little bit more general type approach, and that's where the critical plane approach comes in. So let me describe what we would have to do if we had general non-proportional loading. Alright, so here's a couple time histories of stresses that illustrate what might happen for a more general non-proportional loading history. We have our little stress block or stress element, sigma x, sigma y, and tau xy. And if you look at these time histories of these stress components, there is no relationship among them. They don't change in phase with one another. They're just kind of doing whatever they're doing. Now this is an example of very extreme type of non-proportional loading, but these things can be programmed into testing machines and we can do them. It is you really have to look for non-proportional loading in general components. The tendency for components in industry in a lot of cases would be for proportional loading, particularly near very critical spots, or maybe hot spots you might call them, for fatigue damage in components. So if you have a hole in a thin plate, if you look at how that structure is loaded, maybe you have lots of different loads, the forces might be changing rapidly, non-proportionally, but the stress state at that hole, the surface of the hole in a thin plate, would be uniaxial no matter what kind of loads you put on it. And so that would be a proportional type stress history. So it's not, I wouldn't say that it's not terribly common, I would say, but there are places that you can find general non-proportional type loading in different components. And definitely we can test materials for this, and definitely we see that we don't get the same response as if we were to assume that it was under a proportional type loading history for fatigue damage. So I have these histories here, and there's a whole lot of things that we have to think about now. If we want to do any kind of data reduction on these time histories, we have to be super careful now because we have all three of them. We don't want to miss a peak in one channel while we have maybe something constant going on in another channel. But the idea here then is that if we were to take a look at a sequence of points in time for these different stresses, we can construct more circles as a function of time, and you can see this Moore circle expanding and contracting depending on the value of the equivalent stress. You can see this the principal axes rotating in the material, and at one point it may be up here somewhere, and another point it may be down here somewhere to get to our principal angle and our maximum shearing stress angle. And it is even possible, if we have a 3D Moore circle that we want to draw, if we have stress components, we may also have a sigma z, and we could have out of plane maximum shearing stresses as well. So what we want to do is we want to have an approach that can accommodate tensile behavior in the plane of the material. It has to accommodate shear behavior in the plane, and it has to accommodate out of plane shear behavior as well. So if you know about 3D Moore circle, then you know about 45-degree out of plane maximum shearing stresses. So all these different planes in the material could be critical planes. They're potential critical planes. So if we look at our stress block from that perspective, and we rotate our stress block between 0 degrees, if we want to call the x direction 0 degrees, and we could go all the way to 180 degrees. We could have normal stresses pulling at each of these different directions, and we could do a fatigue analysis on each plane in every single one of these different directions. Now the 0 degree and the 180 degree direction are the same, so I guess if we want to show this with symbols, let's say possible critical planes. Are with the bracket here 0 to 180 degrees with that bracket over there. Well, we have a practical consideration now to think about. We have an infinite number of planes between 0 and 180 degrees. So what we're going to do is we're going to partition 0 to 180 degrees into a finite number of possible critical planes, with the hope that we haven't missed fatigue damage significantly on one of the critical planes that are in between the ones that we've picked. So for example, if we do every 10 degrees for a potential critical plane, we would have 18 planes from 0 to 180 degrees. If we do every 5 degrees, we would have 36 potential critical planes that we would resolve the stresses on using stress transformations and calculate our fatigue damage. And I'm saying stress, but fatigue damage parameters may also depend on strain as well as stress. So we may also have to resolve our strain as well. Let's say we're going to do every 10 degrees. Okay, so what we would do is we would have our baseline case where our stress block is oriented at 0 degrees. We would do another case where we have this stress transformation done at 10 degrees. I'll put in our stresses here. Okay, so this would be sigma x prime at 10 degrees, and we would do this for all of them, and we would also want to get the strains in this location as well. So not only do we want sigma x prime, we also want epsilon x prime, and we might have a damage parameter that depends on normal stresses and shearing stresses, kind of like a Findley parameter. So we might also have to find tau x prime y prime and gamma x prime y prime at each of these angles in between 0 and 180 degrees. Now this brings us up to another point. If we need strains and we have stresses that have been measured, well, we're going to have to calculate the strain somehow. If we have any kind of plasticity at all, we're going to have a multiaxial cyclic plasticity model that relates stresses and strains. A multiaxial cyclic plasticity model is the tough part, in my opinion, in all of this, because we need to have a very good model that doesn't overestimate strains, or if we're measuring strains and calculating stresses, doesn't overestimate stresses, because they can have a big effect on our calculated fatigue life. So one way or another, we need a way to relate stresses and strains. Now, if we do a multi-axial plasticity model, we can start with our baseline sigma x, sigma y, tau xy, and take that time history of these stresses and calculate the time history of the strains, and then do our resolving to these potential critical planes. Some materials, as I mentioned, are sensitive to shearing stresses and shearing strains, so we may do a normal stress sensitive fatigue damage parameter on the planes where the crack may grow perpendicular to that stress direction, but we also may need to do a different damage parameter where we might have a shear crack that forms along this direction. Okay, so now we have 18 planes for normal stress. We have 18 planes for shear stress in the plane. We have 18 candidate critical planes for shear stress out of plane. So 45 degree out of plane. Direction. So if you don't know anything a priori and you want to go every 10 degrees, now you have 36 different fatigue calculations that you have to do, which includes rainflow cycle counting, in evaluating the damage parameters, accumulating damage, and determining the life that you might have. So it gets very involved very quickly, and this is only for one point in a component. If you have a finite element mesh and you have a huge number of points that you want to do this in, well, you have 36 fatigue calculations multiplied by the number of hotspots that you might have, or in the worst case, maybe the number of nodes if you want to do a complete kind of like a life contour if you're trying to do some optimization or something like that. All right, so there's a lot of things going on. Now that's kind of the overview. So after we do the fatigue damage calculation on all of these potential critical planes, then the plane that experiences the most damage according to our damage parameters that we've used is the final critical plane, and that would be the one that we would identify as the cracking direction for our particular component. Now this assumes that there's not any interaction among these planes. Could there be? Well, sure. If you have a crack that forms, there can be interaction and stress shielding in certain directions. So this is typically taken as a crack initiation approach and not a crack propagation approach. Now, crack initiation means different things to different people. It could mean 1 millimeter long crack. It could mean 1/10 of a millimeter long crack. But those kind of details, as long as you're consistent and you don't have a crack that you think significantly influences the stress distributions, then I think this is a great approach to use for an estimate of fatigue life and crack orientation, crack development. All right, so let's give kind of an overview and a flowchart sort of way of what you might need to implement a critical plane fatigue damage model. All right, so the first thing we need is to identify a place that we're interested in doing this calculation at. And even that itself can be a process. But suppose we have that and we know the stress state and how it changes as a function of time. Here I'm just drawing a plane stress state because it's easy to use and it's pretty typical. As I mentioned, we could do this for a fully three-dimensional stress state if we want. We could have more candidate critical planes in that case as well, though. So we do need a stress history, or we can start with a strain history or vice versa. But and eventually we would want to find both the stress history and either calculate or somehow obtain the strain history as well. So we have epsilon x, epsilon y, and gamma xy then as a function of time. So in this section comes a plasticity, a multi-axial plasticity module. And all the things that go into that. The material properties you might have to worry about, and what type of hardening, isotropic or kinematic, all these good things. And I do teach a class in plasticity where we focus on multi-axial cyclic plasticity just for this purpose. Next thing that we need to do is we need to identify the damage parameters that we might use. Now there are several common uniaxial fatigue damage parameters that people have used in critical plane approaches. I think there are some new ones that have come out since then that might be more suitable for multi-axial type fatigue. But people still use things like the Smith-Watson-Topper damage parameter, or a Fatimi-Sosi type damage parameter for shear that incorporates a little bit of normal stress or normal strain. But we need those damage parameters, and so these are typically functions of, well, in general, sigma and epsilon, the normal stress and strains, and maybe gamma and tau, the shearing stresses and strains. But also they have fatigue properties that need to be obtained as well. So these can be strength coefficients, fatigue strength coefficients, fatigue ductility coefficients, exponents, elastic material properties. So those need to be dealt with as well. All right. So we have these stress and strain history now. We have the damage parameters. We need to resolve the stress state to candidate critical planes. I'll use this as the tensor. All right. And how many planes you want to use. Do you want to use shear planes? Do you want to use out of plane shear planes? All those things you have to account for. And then you have to do your fatigue calculation on those candidate critical planes. Now the fatigue calculation on these candidate critical planes is like doing a uniaxial fatigue calculation. You have to do rain flow cycle counting. You have to identify cycles that occur on these planes. You have to accumulate damage and the whole bit. And so you have to do it on each individual candidate critical plane if you have general multi-axial non-proportional type loading. The current state of the art is it's just not possible to be able to identify a damaging event overall as compared to a particular candidate plane. So let's write in here rain flow, and part of the rain flow is peak picking and rearranging the time history and all that kind of good stuff that goes in here. Damage calc, and then accumulate damage. And then it gets easier after this part. Then you just need to identify the plane that experiences the most calculated damage. And then that would be your critical plane and your expected cracking location. Alright, so without getting into a lot of the details, that is an overview of the critical plane approach to multiaxial fatigue. There are a lot of very important details in this, but we'll try to tackle those in some separate discussions.